What is a sensor? A sensor is a device that measures a physical quantity and converts it into a signal which can be read by an observer or an instrument. Some examples of sensors we use every day are thermometers, automatic door openers, smile detectors that are used in cameras, and GPS systems. Sensors in cell phones. Sensors are what make smartphones smart. Most Android or iOS powered devices have built-in sensors that measure motion, orientation, and various environmental conditions that are capable of providing raw data with high precision and accuracy. For example, a game might track readings from a device's gravity sensor to infer complex user gestures and motions like tilt, shake, rotation, or swing. Likewise, a weather application might use a device's temperature sensor and humidity sensor to calculate and report the dew point. Or a travel application might use the geomagnetic field sensor and accelerometer to report a compass bearing. Types of sensors. Most platforms support three broad categories of sensors. 1. Motion sensors. These include accelerometers, gravity sensors, gyroscopes, and rotational vector sensors. 2. Environmental sensors. These include barometers, photometers, and thermometers. 3. Position sensors. These include orientation sensors and magnetometers. We compared two motion sensors and a position sensor on our devices for conducting various activities. The sensors we used were accelerometer, gyroscope, Teslameter. Let us look at how these sensors work individually. An accelerometer is a device that can measure force of acceleration, whether caused by gravity or by movement. For example, this is a screenshot of an instance when the device lay flat on the table. The acceleration in the x and y directions is approximately 0, but the z-axis is acceleration due to gravity, whose magnitude is 9.8 meter per second square.
Device movement along the x-axis causes changes in the red graph, whereas the green and the blue remain fairly constant. Movement in the right direction is positive and in the left is negative. Similarly, movement along the y-axis leads to changes in the green line. Forward is positive and backward is negative. Lastly, movement along the z-axis corresponds to change in the blue line. Upward movement is positive and downward is negative.
A gyroscope is a device for measuring or maintaining orientation based on the principles of angular momentum. Unlike an accelerometer, which measures the linear acceleration, a gyroscope measures the orientation directly.
It depicts the changes in the angular momentum or the orientation. Rotation about the y-axis is depicted by the blue line. Rotation about the x-axis is depicted by the green line. The faster the device is rotated, the greater is the magnitude of the rise or fall of the graph. Rotation about the z-axis is depicted by the red line.
A Teslameter is a magnetometer for the measurement of magnetic induction or magnetic field intensity. The most common Teslameters are based on the induction principle.
Magnetic heading is represented by the red graph and the true heading by the green graph. Here, we have only illustrated movement along the xy plane, and the corresponding changes in the magnetic field are shown by the green and the red lines. The numerical values of true and magnetic headings gradually decrease from 360 to 0.
The accelerometer's blue line depicts the slight changes along the z-axis, which are due to the motion against gravity while walking. At every turn, the sudden change in angular velocity causes the gyroscope to show changes in its blue line. The general movement is in the xy plane, which is denoted by the Teslameter's green and red graphs. At every turn, the Teslameter's readings change by 90 degrees. As the major movement is up and down, we can see bumps in the accelerometer's blue line, which is the z-axis. The gyroscope shows changes only on the turns as that is the only moment throughout this activity when angular momentum is provided. Again, for every turn, changes of 180 degrees are recorded in the Tesla meter's readings. The magnetic and true heading, which is shown by the red and green graph, is exactly the same except for a phase difference. The major changes are only in the z direction, and these are represented by the blue line of the accelerometer. There are no significant changes in the gyroscope's graph due to lack of rotational motion of any kind. Changes in the magnetic and true heading are represented by the green and red lines of the Tesla meter. The major changes in the accelerometer are in the y and z directions, which is represented by the green and blue lines. Changes in the x-axis are due to the imperfect motion of the swing, which we are neglecting. Again, there are no significant changes in the gyroscope due to lack of any rotational motion. The general motion is along the zy plane, and thus these changes are represented by the green and blue line of the Tesla meter. After comparing all the sensors for different activities, we see that every sensor has its own use. An accelerometer is essential for detecting any kind of motion, however, it will lag, that is, be inefficient in detecting rotational motion. A gyroscope is essential for detecting rotational motion, and thus, combined with an accelerometer, it can be very useful. A Tesla meter is required for detecting positional changes, like a compass can work only if a Tesla meter is present. We noticed that the gyroscope was not of much use as it only detected a turn, whereas the Tesla meter distinguished between a 90-degree and a 180-degree turn. The most efficient out of these, for the activities we performed in particular, would be the accelerometer.
We will now discuss the tools we used in making this video. Sensor Emitter. It is a Windows Phone app which sends data from the mobile sensors to a computer and comes with a C# file to set up the TCP server and show a 3D projection of mobile's orientation. Now, there aren't direct ways to screen capture mobile devices, so we came up with the following solution. We used an iOS app called Sensor Streamer which plots graphs for accelerometer, gyroscope and Tesla meter on the same screen. To screencast the iPad, we used its inbuilt function AirPlay, which is actually meant to screencast its screen on HD TVs using an Apple TV. But we instead used an application, Reflector, which mirrors the iPad screen onto the laptop using the same function AirPlay. We then screen captured the laptop, which was now showing the iPad screen. You must have noticed that we performed our activities near the laptop. This is because here the screencast was being sent through Bluetooth, that is, wirelessly, which is not a very efficient way of sending high definition videos with fast frame rates. This is also the reason why you would have noticed small time lags in the graphs, which are a consequence of loss of video frames. The video editing was done using Final Cut Pro 10. Thank you for watching this video.